Actually, the college professor wells up in me and is telling me that I should probably give you a pop quiz at the end of the class. And I must say that Kent's introduction certainly fans those flames because he portrayed a very incorrect statement about what science is. What I see as the foundation, the key to understanding this conflict, lies at the various deepest levels in the philosophies of science and religion, that is, in the metaphysics of the contrasting philosophical systems. So what I'm going to say for the next few minutes is going to sound like Philosophy of Science 101, although unfortunately our students rarely take such a course. I also point out that I use the word metaphysics not in the sense of listening to New Age music, burning incense, and eating vegetarian pizza, but rather as that area of philosophy that deals with first principles, with those things that cannot be deduced or proven to be true. We simply take them to be true by assumption or supposition. We might say, for example, let's suppose that the geological forces of erosion, volcanism, glaciation, etc., that we see operating today have always worked in the same way. What could we learn from this? What would this lead to as a set of inferences about the Earth's history that may seem sensible? We can't really defend these assumptions, and Kent has pointed this out. We can't prove it to be true. We can't simply make it a part of our, we can simply make it a part of our philosophical system and see how successful that system is in leading us to new discoveries. This is essentially what geologists did in the late 18th and 19th century, and this led to the very first inkling that the Earth must be a pretty old place. At the base of science, I think, is a very small and clear set of first principles, the metaphysics of science. And that leads to the so-called scientific method. If I could have the first overhead. This is one scientist's statement as to what scientific method is. He says, in general, we look for a new law by the following process. First, we guess. Don't laugh, it's really true. Then we compute the consequences of the guess to see if this law that we guessed is right, what it should imply. Then we compare those computation results with nature, we say, to experiment or experience. We compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make any difference how smart you are, who made the guess, or what his or her name is. If it disagrees with experiment, it's wrong. That's all there is to it. This short, whimsical, even facetious statement is actually a fairly concise and complete statement of the scientific method, as simple as it is. One of the most interesting phrases in Feynman's description is, quote, first we guess. A very confusing issue we must deal with straight away is that of what it means to say evolution by natural selection is a theory as opposed to a hypothesis or fact, or even a guess. Nowadays, scientists pretty much use the words theory and hypothesis interchangeably, and even the words conjecture and yes, the word guess is synonyms for theory and a hypothesis. Steve Gould made this very important point in his talk last week when he pointed out that there is no hierarchy where guesses are promoted to hypotheses and hypotheses elevated to theories and theories elevated to natural laws. They're all really guesses which have been tested against empirical evidence or not tested. And if they've been tested, they've been falsified or not falsified. But it is equally true that a guess, hypothesis, or theory that has been tested and not falsified has to some extent been corroborated, that is found to be useful in explaining some sets of observations and pointing to new experiments that we might do. In that sense, some theories are better than others, and in that sense, if someone were to ask me if evolution by natural selection were a fact, which often happens, I would say, of course not. But it is not merely a theory. It is one that has withstood test after test after test without being falsified. I repeat, without being falsified. It is in the secular pantheon of scientific theories, that is, natural selection theory, along with quantum mechanics, relativity, atomic theory, continental drift, and a few others. But none of these theories are facts. Here are what I think are roughly the first principles of science, if we could have the next overhead. The first one, Kent referred to somewhat derisively, that natural law acts the same way at all times and in all places. This is a first principle of science. It's not something that we can prove. This is the idea that I alluded to above that seems to have been derived from the ideas among geologists of the 19th century, and it's the idea that they called uniformitarianism. Implicit in this is that science doesn't deal with miracles, because miracles by definition involve circumstances where natural law is set aside. Now, conceivably, science could determine whether a miracle had taken place, but I even doubt that. For example, someone might make the claim that so-and-so had arisen from the dead, and we might apply a scientific analysis to determine that the person in question was in fact once dead and was now in fact alive. But even here, we would want to be very wary of a possible hoax, substituting, for example, a live identical twin for the dead person. So even here, I would want to see maybe 3 replicates with proper controls. And this is what religion, which does deal with miracles, cannot provide for us. Second principle. Hope that's in focus. Scientific observations are repeatable. This arguably is more a corollary of the uniformitarianism principle than a distinct first principle, because it follows that if natural law acts the same way at all times and in all places, that I or anyone else can repeat the experiment. When I submit a paper to a scientific journal for publication, it always has a materials and methods section that describes exactly what I did to get that particular result. If it doesn't have a materials and methods section, it would be immediately rejected. In contrast, one never sees a materials and methods section in a religious tract. It just doesn't work that way. Third principle. Scientific theories must be testable, and to be more explicit, they must be falsifiable. And this is the heart of the scientific method. I alluded to this a few moments ago, and this is perhaps the central tenet of the scientific method. Popper's so-called line of demarcation between science and non-science, between science and religion. Implicit in this is that a scientific theory must be tested, or must be stated, in addition to being tested, it must be stated with sufficient clarity, precision, detail, and internal consistency that one can deduce singular, unequivocal predictions from the theory that are testable against the empirical evidence. The book of Genesis suffers badly in this regard. Fourth principle. There's a web of interconnectedness and internal consistency Theories in all branches of science must be consistent with all the theories and empirical evidence in all other sciences. Thus, the theory of evolution by natural selection must be consistent with genetics and cell biology, but also with geology and physical chemistry and so on. If this isn't true, there's something wrong with one of the theories or some of the data. So a really interesting example of this involves the history of Darwin's theory itself. Which, although somewhat initially successful, that is Darwin's theory, the publication of the joint Darwin-Wallace papers in 1858 and the publication of The Origin of Species in 1859, Darwin was essentially dead by the year 1900, so proclaimed by Alfred Wallace himself. Why was it dead? Because it was inconsistent with a widely accepted theory of the age of the Earth and an incorrect theory of inheritance based on the notion of blending inheritance. The theory of the Earth's age was promulgated by Lord Kelvin of the temperature scale, one of the most prominent physicists of his era. Had actually miscalculated the age of the Earth based on its rate of heat loss, giving Darwin only 24 million years for evolution, which even Darwin thought inadequate. It turned out that the physicists based their calculations on an incorrect theory, and that Darwin was right when he wrote in a letter late in his life that he somehow sensed the age of the Earth was greater than Kelvin had allowed. Kelvin made his calculations very shortly before actually, the discovery of radioactivity, and the vast store of energy in the nuclei of atoms had not been taken into account in his calculations. The problem of blending inheritance, which Kent alluded to also, is the problem, not the blending inheritance itself, is that selection operates on genetic variation, and it certainly does. But as sexual reproduction blends away variation, as Kent suggested, there would be nothing for selection to operate on, and this indeed would be a problem because Darwin's theory requires that genetic variation exist in populations, and it comes into existence in population. But this was a falsification, as it were, of Darwin's theory towards the latter part of the 19th century, and Mendel's theory, which was rediscovered in the year 1900, provided a sound genetic foundation upon which a theory of natural selection could operate, and actually led to the rebirth of Darwinism, which is being so intensely battled by creationists today. Final point is that scientists are reductionists. That is, all natural phenomena can be explained in simpler terms. And I would say that scientists are incorrigible reductionists. This may not exactly be a first principle of science, but it's certainly part of the sociology of science, the culture of science. Biologists have insisted for a long time that the whole of life, meaning essentially the activities of cells, could be understood in terms of chemistry. And this has been dramatically confirmed in the past half century or so, and particularly in the past 2 decades with the extraordinary progress that has been made in cell biology, which is now pretty much called molecular cell biology. So life, as we understand it, is reducible. I now want to just take a few minutes to briefly walk through the major classes of evidence, much as Kent did, that bear on the origins of species, the diversity of life in all of its complexity and all of its seeming adaptedness. On the one hand, and I want to look at neo-Darwinism, the theory of evolution, in contrast to creationist theory, in context of these metaphysical principles. On the one hand, we have neo-Darwinism that claims that the whole of the diversity of life evolved from a single or from a few initial forms, primarily by a process of